Good morning. My name is Eric Walker, and it's my pleasure to be able to welcome you to Orkney International Science Festival and Foraging Fortnight online. The Orkney International Science Festival is having its 30th anniversary this year, and we are marking the occasion with our very first online festival. This year, we are delighted to be bringing a full and diverse festival programme directly to you wherever you are. I'd just like to briefly introduce this morning's speaker to you. Dr. Mark Cooper is a retired biology professor from the University of Washington in Seattle. His doctorate is in biophysics from the University of California at Berkeley. Mark's interests in standing stones began back in 1986 on his first trip to Scotland, when he was working as a space and gravitational biology postdoctoral fellow with NASA. After visiting Orkney in 2018, his interest in standing stones was rekindled. He began researching representations of hydrodynamics in Neolithic art, naval transport, and the nautical engineering of prehistory boats. His talk today is aimed at tying these threads together and has the tantalizing and tempting title, Sailing on Stones. If you have any questions or comments for Mark, please enter them in YouTube's live chat. They will then be passed through to here by some mysterious process, and we can discuss them after Mark's talk. Enough from me. Here is your speaker for today, Dr. Mark Cooper.
Thank you very much, Harry. Today, I'd like to talk to you about on the topic of sailing on stones, the evolution of megalith ballasted boats in the Neolithic. The concept is that Neolithic mariners may have developed a better means of ballasting their boats to advance maritime transport. The concept is that of a keelstone, a megalithic appendage to a boat, which would serve as a counterweight to a multi-ton cargo. Next slide, please. So defining a hypothetical time period of the age of keelstones between circa 4300 BCE and 1800 BCE, this is the time period where we're hypothesizing that megalithic stones were used as an external ballasting system. The history of ballast goes back to perhaps 1 million BCE. In fact, during the entire period of seafaring, from the earliest rafts to the present time, ballast is a critical part of ballasting or trimming the position of boats in oceans and other bodies of water. So throughout history, various types of ballast have been used: stones, sand, wooden keels, concrete keels, metal keels, and finally seawater ballast. Today, about 7 billion tons of seawater ballast are used per year to ballast the cargo ships that ply the world's oceans. Next slide, please. This is a reconstruction of a Viking longship, the Draken. It's ballasted with 21 tons of ballast stones. That's 7 cubic meters of stones. Next slide, please. So what gives the stability of Viking boats is a combination of beam and ballast. Beam being the width of the boat, and ballast, this heavy weight that's been placed in the hull. Next. Well, what is the backstory to this ballast? To answer that question, we need to go back in history about 5,000 years. Next slide, please. This takes us to the 4th millennium, 4000 to 3000 BCE. This was a time of major change in Northwest Europe. Neolithic farmers and pastoralists were crossing the English Channel, colonizing Britain, Ireland, Orkney, and the Shetlands. By the end of the fourth millennium, a new culture had arisen in Orkney, the grooved ware culture, distinguished by its pottery and the use of elongated megaliths in astronomical and funerary monuments. So during this period, it was characterized by colonization, maritime transport, and sailing ships. In Orkney, there are monuments such as Maes Howe, and inside this tomb, there are stones that resemble the keels of boats. So throughout my talk, I will refer to these stones as keeliform, keel-like in shape. Next slide, please. So to discuss ballast and ballasting, it's useful to look at the hydrodynamics of rafts, also known as balsas, which is the Spanish word for boat. They're highly adaptable modular watercraft. And it's believed that they've been used since the earliest times of seafaring. For instance, the first Mariners project hypothesizes that triangular rafts were used to transport settlers from Indonesia to Australia, circa 50,000 BCE. Much more recently, around 3000 BCE, Neolithic farmers in Switzerland in the upper Rhone River Valley constructed two triangular cairn funerary monuments. Do these monuments represent triangular Neolithic rafts, boats? So when we look at many types of vehicles, organisms that move through water, move through air, or vehicles that move through water or move through air, we're dealing with similar types of physics. All of these agents are flying through fluids. Next slide. So two key principles that we need to be discussed are buoyancy and steering. Next slide. So if we look at buoyancy and steering as a conceptual lens to start analyzing prehistory watercraft, we'll do a comparison between modern inflatable boats and possible Neolithic boats. So in the upper part of the slide, you see a modern rib boat. That's a rigid inflatable boat. It has a metallic hull, and it's floated by a set of pontoons. Air being the most effective type of flotation available. So on the right, you see another inflatable boat, but this time it doesn't have a solid keel, it has an inflatable keel. So if we look at Neolithic monuments, and this is a cairn, a passage tomb in southwest Britain known as the West Tump Long Barrow, you see a trapezoidal shape. What I've done is I've outlined a set of spars, hypothesizing that this may be the outline of a Neolithic rib boat. And so to form the hull, what I've done is taken a stone from Stonehenge, a blue stone, stone 63, and in Photoshop, I've lashed it to a longitudinal spar known as a keelson. So the stone is suspended from the keelson. And to further support it, put some cross beams. And in this way, we've constructed a boat that has the same type of force balance and torque balance that you would find in a rib boat. Next slide, please. So to discuss the issues of prehistory boats, we need to look at flotation, propulsion, stability, and speed. And to do that, it's useful to use hybridized associations, drawing from the theory and experimental approaches of several disciplines, such as nautical engineering, archaeology, and physics. We can call this intersection NEAP. It's a type of interdisciplinary analysis known as STEAM, a broader set of interdisciplinary analysis which involves science, technology, engineering, arts, and mathematics. So using NEAP and STEAM analysis, let's take a look at possible Neolithic watercraft that could be been used in both good weather or bad weather. Next slide, please. So I'd like to first discuss perhaps one of the most advanced forms of keelstone, and I'll use that term interchangeably with keeliform stones. This is, again, a hypothesis that these stones that look like keels may have acted like keels. So this is a Devil's Arrow megalith. They're among the largest megaliths in Britain. This one's about 30 tons. It's in Yorkshire. You'll note that it has a set of longitudinal grooves, more frequent at the apex of the stone. Each of the three Devil's Arrows have these longitudinal parallel grooves, and they resemble the strakes on a rib boat. Strakes are the grooves or the flanges that you'll see on boats, stubby wings on planes, missiles, and spacecraft are also known as strakes. You'll also find strakes on modern watercraft like this Kingfisher trimaran kayak, and you'll note it at its ends it has fluted strakes, which resemble the type of fluting construction of the grooves that you see here in the Devil's Arrows. So these fluted strakes provide hydrodynamic benefit to the stone and to the watercraft, and also in aeronautical engineering to flying machines. Next slide, please. So why would you want to place strakes on the bow of a ship? As you move a boat through water, you're going to create a bow wave. It's displacing water upwards and sideways. Next slide. That produces drag and slows down the ship. If you want to go faster, you can redesign the bow or prow, which is the apex of the bow, such as this Bronze Age ramming prow, which was anchored at the apex of a Mediterranean warship. So you'll note the similarity between the strakes and the water channels in the ramming prow and that which you see on the Devil's Arrows. Next slide, or next increment. So these strakes and water channels improve the hydrodynamics of bows during wave impacts, and that's something we'll discuss in a few moments. Next slide. Now, the Devil's Arrows are megaliths, and they are arranged in an alignment that points in the direction of north-northwest towards a group of hinges about 15 miles to the north-northwest, known as the Thornborough hinges. Those hinges are culturally connected with the hinges in Orkney as well as Stonehenge. The Devil's Arrows are also pointing towards a ford in the River Uri, which is very close by. Next increment. And that ford is now crossed by a bridge of the A1 motorway. So this point in the Uri River may have been a transshipment point back in the Neolithic or perhaps even the Mesolithic. It's an important part even today of the transportation system for the UK. So this alignment of stones, these may be repurposed keelstones, and their arrangement may have been there to mark this important transshipment location. Next slide. So as I mentioned, these Devil's Arrows and the hinges at Thornborough connect culturally to Orkney. These are the stones of Stennis, a stone circle near the Ness of Brodgar. And as from a read of archaeological literature, it's believed that the stones of Stennis and its henge may have been the first henge in Britain. So the hypothesis is if these keeliform stones were actually keels of boats, that this may be a display of Neolithic nautical engineering, displaying keelstone technology. So if we compare the morphologies of these stones to modern keels, we can see that these stones may reflect a diversity of keel morphologies. For instance, a full keel or deep keel, as well as a fin keel. And on modern yachts, these types of fin keels are commonly used to ballast the boat and increase its trekking. Now, a stone is actually quite lightweight. It's compared to the keels on modern yachts, which are made out of lead. So stone is 3 times the density of water, whereas lead is 11 times denser than water. The lead fin keel is attached to the hull with steel bolts. I envisioned that the stone keels, the Neolithic world, could have been attached with leather or hemp ropes, attaching them to a keel on its dorsal or back side. Next slide, please. So what could have been used to float these boats? To do that, let me take you to the Western Hemisphere, the pontoon catamarans of the Chango sea hunters in northern Chile. This is one of the most successful watercrafts of all time, and this form of watercraft is at least 3,000 years old and may predate that by many thousands of years. It's constructed from the skins of adult sea lions. It's virtually unsinkable unless it's punctured. The Chango sea hunters hunted large fish, swordfish, tuna fish, sharks, even whales. If we take the pontoon catamaran made from inflated animal skins, and we take a keeliform stone, say from Stonehenge or Skara Brae, we lash it to a keelson and then suspend it from the lattice work that's found on the Chango raft, we can construct a hypothetical European Neolithic raft from this, which is very stable. Next slide, please. So we talked about the hypothesis of keelstone in the context of flotation. And now what could be done to help integrate this technology into seafaring? To do that, we need to look at or get into the grooves of grooved menhirs, such as the setter stone on the Isle of Ide in Orkney. So what we may be looking at are regional typologies and text stories in stones. Using these 3 visual databases, I looked at about 3,000 elongated stones in Britain and was able to locate about 100 that had these longitudinal grooves. Next slide. Now, to the west and south of Orkney, southeast of Glasgow, is the Glessart stone. It's a much smaller Neolithic stone which has grooves in it. And it has some features that are very instructive about how these grooves were made. You'll see an X-like incision on its apical surface, a couple of other linear incisions, etchings, and there's an apical groove that's contiguous with a longitudinal groove. There's no watershed on this rock, and there's no evidence of erosion, which brings up an important issue. Many people who see these stones, bloggers who comment, assume that these grooves were made by rain. But it's not possible with the random actions of rain, and rain is only impacting the stone at 200 psi, pounds per square inch. Pressure washers have 2,000 pounds per square inch, and you cannot etch concrete with a pressure washer. So conclusion is that the next slide, or next increment, that these grooves must have been carved by humans. But for what purpose? Next slide. So if you look at these longitudinal grooves on the setter stone, as well as the devil's arrows, they resemble the loading lines that you see on modern cargo ships. And the reason for these loading lines is to make sure that the boat is not overloaded or underloaded. They are calibrated for operational stability. If you overload a ship, you will destabilize it. And if this is an issue of torque balance, and if you overload it and the ship is poorly designed and lacks reserve buoyancy, it will turn and began to capsize and suffered the fate of the Vasa warship, which was discussed in an earlier presentation in this festival. An interesting aside, loading lines were required by law on Minoan cargo ships in ancient Crete, circa 2500 BCE. So the utility of cargo lines for a seafaring culture are very important. Next slide. So when I came to Orkney 2 years ago, I had just visited Stonehenge and was headed north. And at Stonehenge, they were describing, next slide, new findings that during the construction period of Stonehenge, animals were being transported from great distances, as far away, I believe, as Scotland. They were arriving in the late fall. Isotopic analysis of the teeth and bones of these animals at Durrington Walls, there was a high prevalence of 9-month-old pigs. So the question is, if these were some of these were Scottish pigs, how were they being transported? Were they being moved in a chain of transport? And we look at journeys along the eastern coast of Britain from Leith to Filey Bay. That's a journey of about 200 miles. And how would you accomplish that with this livestock? Next slide. Well, one of the watercraft that most likely would have been used was a carrack, also known as carragh. It's a wicker boat with leather hull, 1 to 3 layers of leather thick, propelled by a leather sail suspended from oftentimes an A-frame mast. But was this the only type of watercraft that would have been used? If you were sharing this type of boat with cows and pigs for 4 to 6 weeks, there's some obvious problems with this. So next slide. So I began looking at whether an inflatable, rigid inflatable boat construction, like I spoke of earlier, might have been useful as a livestock transporting barge at this time period in Neolithic Britain. So to do that, I reconstructed a devil's arrow using a metal file embedded in a modeling clay matrix. I baked the file into this clay, grooved it to match the grooves on the devil's arrow. And this 300-gram keelstone, suspended it from a keelstone, and then added 2 pontoons, some plastic water bottles. Next slide. Oh, so when you construct a craft, you have to anticipate that this watercraft must be able to withstand 50 to 100,000 wave impacts as it moves from Scotland to Stonehenge. Next slide. So the hypothesis is that a keelstone is an ancient mariner's tool, which enhances the boat's ballasting, its tracking, which means to move straight in the water, and its ability to pierce oncoming waves. Next slide. So I've made a YouTube, and Howie Firth asked me to post that on YouTube, and he'll have a link to it. So if you want to see these movies of a sea test of this type of raft reconstruction, I can tell you that in Puget Sound, it does quite well. No capsizing, rides the waves and pierces them, quite well. Next slide. So in terms of maintaining motional stability, using a keelstone and with a 3-to-2 ballast to cargo ratio seems to do the trick. So it provides the adequate force balance and torque balance if you're using one of these keelstone ballasted balsas. So to understand the hydrodynamics of rafts, especially in Britain during late November, if you're moving animals, we can draw on historical accounts of rafts other places in the world, such as Peru. Spanish historians documented the construction and dynamics of Peruvian trading rafts moving from Peru up to Mexico. And one of the things that you find from this analysis is the bow shape is critical, but what about the stern? Next slide. So if we look into the Neolithic at Neolithic monuments, let me take you to Western France, the Gulf of Morbihan. This is the Arzon Passage tomb, which is constructed around 4000 BCE. In terms of ballast and ballasting, this monument has it all. There are so many features which are of particular importance. First of all, the stones that construct this stepped flat pyramid cairn are similarly shaped. Were they internal ballast stones from cargo ships, which had displacement hulls? When the tomb was excavated, there were two large keeliform stones at its entrance. The one on the left resembles the keel of a modern yacht. The one on the right is L-shaped. Both of these may have been used as keelstones. The L-shaped keelstone resembles that of a shoal keel, and that's positioned midships. But it also may actually have been used in the aft region of the boat. Next slide. As a skeg, and a skeg is an appendage. It's like the bottom part of the tail fin of a fish, and it's there to provide tracking. And in a kayak, it plays a very important role. And so the question is, to skeg or not to skeg? That is the kayaker's question. It's also an ancient mariner's question. What type of appendages are you going to insert below the waterline, the business end of the boat, to keep it going straight, especially when it's confronted with forces like crosswinds? In the case of a modern kayak, you can pull a lever and position a skeg either partway into the water or full way into the water to provide a counter torque to prevent you from torquing in response to the wind. In the case of many boats, especially motorized boats, the skeg is a fixed appendage. It's there to protect the propeller, but its main purpose is to increase the tracking of the vessel. Next slide. So we take a Peruvian balsa, and instead of having wooden dagger boards as steering devices, what we could use is the Neolithic L-shaped stone, which is of unknown purpose at this point in time. But if we do a Photoshop experiment and place it at the stern of this Peruvian balsa, it may have served as a skeg. And this is something I think is going to be of particular importance to archaeologists. I've identified over a dozen of stones which I think are skegs throughout Britain. Next slide. Now, even though the concept of a skeg could have been derived from looking at a fish or a shark back in the Neolithic, and then this bio-inspired technology inserted into rafts, today it's being used on thousands of surfboards and paddleboards. You can buy a $15 plastic skeg, glue it onto your surfboard or paddleboard, and it's detachable. So the question of to skeg or not to skeg is actually being carried out by thousands of people with their personal watercraft today. Next slide. So I've talked about the nautical engineering and physics of keelstones. Now I'd like to talk about their possible cultural significance. To that, we can look for information in Neolithic art and architecture. Next slide. So in the Gulf of Morbihan, the passage tombs, a number of them have vertical stones known as orthostats, which have motifs and carvings of boats, boat parts like steering oars. And as I look at them, they appear to have instructions on how to use these boats and parts in various situations. So I think there's good evidence that these passage tombs, one of the thematic pieces of information that was stored there was nautical engineering in nature. Next slide. So what about the period of around 3000 BCE? In Orkney, in the Maes Howe tomb, passage tomb, one of the last chambered tombs built in northern Britain, the main chamber has 4 cuneiform stones at each of the corners, 1 stone at each of the corners of the main chamber. And this type of cuneiform stone is seen over 1,000 miles to the south in southeast Spain in the De Soto dolmen. You'll see several cuneiform stones in this passage, which, similar to Orkney, is illuminated at a specific time during the year. We also see cuneiform stones at Stonehenge in an astronomical alignment. In the inner horseshoe ring, the blue stones, which are now known to have been transported from Wales, there are 4, maybe 5 stones that are cuneiform in shape. One of those is stone 63. So there are what appear to be symbolic keelstones in both funerary and astronomical monuments. Next slide. So I'd like to borrow a line from Ian Fleming. Diamonds are forever. Ballast stones are forever. Keelstones are forever. Throughout the world, archaeologists are now finding that ballast stones provide an important source of information about seafaring activities. For instance, in America, archaeologists are finding ballast stones in the Jamestown settlement in Virginia. And it helps track some of the early voyages of the English settlers, where they were going, the Antilles, Bermuda. And these voyages help understand what type of cargoes that the settlers were probably carrying and the times at which these events were taking place. So these cuneiform stones, which are prevalent in the grooved ware culture, not only found in Orkney and Yorkshire, but also in the Hebrides at a site called Callanish. It was back in 1986 when I first saw these stones. I recall, like most people, when you see these stones, are staggered by the splendor of them. But I recall seeing stones at that time that reminded me of the keels of boats, but I put that thought aside for many decades, and it wasn't until I went back to Orkney, or went to Orkney 2 years ago, that I began to connect them possibly with seafaring. So in summary, the hypothesis that the presumed functions of these stones in seafaring would be ballasting, tracking, and wave piercing. But after their use as keelstones, they may have been repurposed to demarcate landmarks, to be used in ceremonial monuments, as well as observational alignments. Of course, these are all hypotheses. They may or may not hold water. They need to be critically analyzed and tested, like any scientific theory. Next slide, please. And so I'd like to end by expressing grateful thanks to the prehistory and Standing Stone photo archiving communities for the rich array of visual textual information that they provided about the Neolithic period. Also, grateful thanks to the organizers and supporters of the Orkney International Science Festival during this extraordinary, difficult time period. Thank you.
Well, Mark, that was an incredibly interesting talk. We seem to have lost Eric for a moment, so I will take over from him. Oh, here he is.
Apologies.
Eric, Yeah, no problem. I hand straight back to you because Eric is far better at this than me.
Mark,
Okay.
thank you very much for that fascinating talk. We're a little bit time bound, but I'm going to ask the tech team to extend this for a couple of minutes because there are some very, very good questions and comments coming. One is, people have often wondered how these large stones found their way into stone circles. How were they transported, from great distances, many, many, many miles away from their final location? Did the standing stones come first? Did the keels come first? Were they sailed to near the location, perhaps?
I believe the idea of using animal floats, inflated animal skins, goes back to the Mesolithic, and that when the Neolithic revolution took place in the Middle East and you had a surplus of animal skins, then you could use inflated skins to make larger boats. Now, why would you want to do that? With more flotation, a string of inflated animal skins, you could carry more cargo. But to do that, you need to ballast. So earliest ballasting could have been ballast bags, animal skins filled with sand or cobblestone. But there's a failure point. When the bag rips, you lose your ballast.
Mm-hmm.
So I think the revolution, part of the Neolithic revolution, the advance up in Northwest Brittany, was the realization that you could take a single megalith and replace a ballast bag, an axial ballast system, with that single stone. So once you have hundreds or thousands of animal skins, and you could stuff them with hay, or my ideal pontoon would be to take an oxhide and stuff it with sheepskins that have been stuffed with hay. Now you have the equivalent of bulwarks. Make it a Titanic-proof pontoon. And it's possible with marine airbags to transport concrete structures the size of a city block. So there's no really limit that you can lift with airbags.
I've got a query. If these megaliths were previously used as keelstones and presumably exposed to seawater, have they got any attached organisms or traces of organisms like barnacles?
You're right. You're way ahead of me on that. That's exactly that's the test. Is we can imagine biological, chemical, and physical marks that could have been left. So, right, any rock that's placed in the water, you would expect barnacle larvae to attach. And foraminifera, these are protozoan, shelled protozoans. They're called the spiders of the sea. You might also find them in these grooves. So looking for shells and or DNA of these marine creatures may give us a key evidence that the stones were actually in water at some point. The other is evaporates, marine evaporates, salts. Magnesium and calcium sulfate may persist in these grooves. Finally, if the stone is a keel, you would imagine groundings, scrapings. So these stone skegs may have scrape marks from being hitting on beaches.
I've got one final question for you, Mark. Has any analysis been carried out with modern hydrodynamic software to determine their hydrodynamic qualities?
That's the next step. And I've taken some model keelstones and 3D scanned them and put them into some STL files. And if anybody would like to take them and put them in CAD programs to make Neolithic rafts, do these simulations, just email me and I'll send you the STL files. We can open source this question very easily.
Cool. Right. There's been a few questions come in and they need answered. So what we'll do, Mark, is forward them to you, and you can answer them at your leisure, and we'll stick the answers back onto the festival website at some time. So
okay,
people who've asked questions won't be getting ignored. I just want to say that has been a most interesting presentation and discussion. Just thank you. Thank you so much for giving us your time and your knowledge. And can I also thank the audience for participating and asking all these very, very interesting questions. And I need to say a very big thank you to our technical team behind the scenes who work their wonders bringing these festival events to you all. Our next festival talk will be at 11:30 this morning, called Women in Shipbuilding. This is the Grimmond Lecture in association with the Women's Engineering Society and highlights the increasing role of women in nautical engineering over the past 3 centuries. This will be presented by Dr. Nina Baker, an engineering historian. I'd also like to take this opportunity to remind you that there are still spaces available for the PD Kirk lunches this week and also at our evening festival club table sessions. If you'd like to relax around our tables and meet some of the festival speakers, do register to join us for the lunches. The links can be found in the description below each PD Kirk lunch event on the festival's website and will also appear now in this live chat. Just click on it and book a place for today. We'd also like to invite you to the festival club tonight, and this link should also be winging its way to you in live chat. Please click on it, bookmark it, and come along tonight. I can say from experience it is great crack. And if you're enjoying the festival, please do like us on Facebook and follow our YouTube channel. And so, from me, good morning and goodbye for now.